Hey folks, welcome to Chapter 7 of Physics 11. We're moving into some information that you don't need to know for Physics 12, but that's not going to make it any less exciting or less important. In fact, this is probably, of all the chapters in the course to teach, probably my favorite, to be honest. What we're going to look at is something called relativity. It's all about sort of the world when we look at light. Moving quickly. We're going to see that light behaves in strange ways, and a lot of the universe actually is quite strange and quite different, and maybe really just darn confusing. But before we get going and jump into Chapter 7, I want to go through with you some feelings that you may experience during the next series of videos. A lot of the feelings you might go through are things that you would learn about in psychology class. They're quite similar to the stages of dealing with grief, but we're going to change it. We're going to say, hey, it's the same for dealing with relativity. A lot of the information, when I first presented in the video, and it's too bad we're not doing this in person, it would be even better. But we'll still have fun. A lot of the information I present to you, you initially are going to look at that information and your brain will just say, nope, not true. It will not like that information. And if you try to explain this stuff to your parents, that's probably going to be their reaction. They'll just listen to it and say, no, that's not true. That's really not what's happening. So there's going to be denial. The second stage of dealing with relativity is going to be anger. Now, I hope nobody gets angry with me while you're watching these videos, because remember that I'm just the messenger. I don't make any of this true. I'm just going to teach it to you. But quite often the second stage, once you sort of believe it, is that it makes you a little bit angry or uncomfortable. And then the really fun stage, and maybe people will do this with me when we have our Zoom meetings, is bargaining. These are the statements where people will go, yeah, but what if? What if this? What if that? And I'd love to point out bargaining when we do this together in the class. So again, hopefully we can do it a little bit in the Zoom meetings. That's the middle of the road in terms of your stages of relativity. Now, I hope nobody gets to this stage, but depression is in there. Again, this is awful, but typically this dealing with grief would be like the death of a loved one or a cancer diagnosis or something like that. I can see how those things would be depressing, but I really do hope that you're not depressed about relativity or physics in general. Maybe the fact that we're not getting to do it together in class, but not just depression about the concept. And then eventually, what you're working towards, if you can, is acceptance, where you sort of look at that information and you say, yeah, okay, fine, let's deal with it. And I think what will happen is, although the concepts in this chapter are really strange, the math that goes with it is really darn easy. So that should help you, I think, move towards acceptance. Although that means the very next video, I may throw something at you and you revert all the way back to stage 1. You go all the way back to denial. So anyways, that said, getting you all pumped up about relativity, let's do an intro lesson. So, special relativity, all about light, but before we do that, we need to talk about sound. The Doppler effect. I think everybody's experienced that. If you don't know, it's like when you're walking down the street and a car goes zooming by, how the sound changes when that car goes by. The source of the sound, or it actually would be true if you went by the car as well. But it's like you're walking down the road, or I'm running down the street and a car goes by and I hear, and there's this change in frequency, a change in pitch as the car is coming towards me as opposed to when it goes by me. So that is called the Doppler effect. We're not going to get into a huge amount of detail with it, although I will show you this. So let's take a scenario where there's an ambulance and it's got a siren that's producing a sound of 440 hertz. It's stationary. You are also stationary and you've got some kind of little measuring device. Maybe you can download an app, I'm sure, on your phone. If the ambulance is stopped, stationary, and so are you, if that siren is actually emitting 440 hertz, then you will hear and measure 440 hertz. probably no surprise. You hear exactly what the siren is doing. But if that ambulance is now racing to rescue somebody who's fallen and hurt their hip, and it goes zooming by you at 90 kilometers an hour, you're stationary, but the ambulance is moving, you're actually not going to hear 440 hertz anymore. You're going to hear a different pitch, a different sound. You would hear 475 hertz. Don't worry about where those numbers came from. There's a big equation that, in fact, I don't even remember how to use this equation. I made these notes long ago. We're not going to get into that part of it. But just know that the frequency changes, that you hear a higher pitch. Now, what's really interesting about the Doppler effect in sound is this scenario. What if we simply flip the script and we make the ambulance stopped, but you're driving by? So you can imagine now that there's an ambulance, they've left the siren on, and you go zooming by at 90 kilometers an hour on the highway. You might assume that it would be the same as this middle scenario, where you go, okay, you flip it around, well, you're going to record 475 hertz. And it's almost 475, but not quite 475. It's actually a little bit different if you're moving and the thing making the sound is stationary. So what we can say for something like sound is you actually can tell who's moving. If we know that somebody's moving at 90 kilometers an hour and the siren is emitting 440 hertz, then we can look at this 475 versus the 472. We know that if you record 475, it's actually the ambulance or the siren that's moving. And we know if you record 472, it's actually you that's moving. So you can tell who's moving. What we call that in physics is we say there's a preferred reference frame. There's actually like a better place to take measurements from. And you can tell when things start to move who's doing the moving. So that's all about sound, and that's sound waves traveling through air. Sound needs something to travel through, right? There has to be a medium. Sound is a wave, just like we looked at in chapter 10. So this is kind of a nice extension, actually, a nice unit to blend in with chapter 10. Sound is a wave, and there has to be some kind of fluid for it to travel through, like a gas or a liquid, something like that. In outer space, where we say, oh, there's nothing in outer space, then there couldn't be sound. And then scientists, they knew all about the Doppler effect. It's an easy one to experience. People figured out the equations that go with it. And then people said, well, what about light? Because light travels as a wave. And when we call empty space empty, we say it's a vacuum. It actually couldn't be a vacuum because waves can't travel through nothingness. There has to be something there for the energy to push against. Remember when we saw those pictures of waves in chapter 10, there has to be like little blue molecules that are able to move to transmit the wave energy. So what scientists did is they said, well, I know we call it empty space, but there actually has to be something there. And they called it ether. This luminiferous ether was the term. And scientists said it has to be a transparent fluid with no friction. We know it's transparent, excuse me, because the sun is millions of kilometers away, and light travels from the sun to Earth just fine. So it's not opaque or solid or something like that. It's transparent, and it's frictionless. And we know it's frictionless because we are on Earth, orbiting around the sun, and if we were orbiting around the sun and there was friction, we would A, generate lots of heat between the Earth and this ether, and that doesn't happen, right? It's not like once a day we're on the leading edge of the Earth and all of a sudden it gets super hot. The other thing that would happen if there was friction is the orbit of the Earth would start to shrink, and we would start to spiral in towards the sun, right? That orbit would get smaller and smaller and smaller. That'd be really bad as well. And that's not happening. So we can say that ether is transparent and that it's frictionless. So there were two fellows in the late 1800s. Their names were Michelson and Morley, who designed an experiment developing something called an interferometer. So I'm going to type that in here. You guys can do a quick sketch of this. I will get you to copy down this experiment, sketch it in your notes, because it is one of the most famous and important experiments in all of science. Not even just physics, but all of science. So these two fellows designed an interferometer. Michelson was kind of a rock star, actually, in the mid-1800s. He was the guy who scientists turned to if they had a theory or an idea, but they weren't quite sure how to design an experiment. He was really, really creative in terms of designing experiments. So he was tasked with designing this thing called an interferometer, which was going to show the presence of ether. It was going to show that although we talk about space as being empty, there actually has to be some kind of fluid there called ether. So before I get too far into this experiment, here's what I need to show you. So this is a little preface to the experiment. We're going to have a swimming race. We got a bunch of swimmers in our linear physics class, and maybe we're tired of listening to a couple of people sort of beacon at each other about who's the better swimmer. So we decide that we are going to host a swim off. We're going to let these two swimmers duke it out. They're going to go at it. We can finally settle the debate as to who's the quicker swimmer. But it turns out these two swimmers in our class that are always arguing with each other, they're equally good, right? Their skills are identical. It's almost like they're the same swimmer, like I've got on the screen. So we go down to the channel. Maybe the pool's closed, right? COVID. So we go down to the channel. We're distancing ourselves properly, don't worry. The channel has some current. And these two swimmers are each going to swim 200 meters. But what they choose to do is take different paths so that they're not sort of overlapping and fighting with each other. So one swimmer decides that they're going to swim 100 meters downstream and then turn around and swim 100 meters back. And maybe there's a little bell they can hit at the halfway point, right? Like a split time. The other swimmer says, well, I don't want to sort of be fighting with you for position in the water, so I'm going to go 100 meters across and then 100 meters back. And there's a bell there for the split time. So there's swimmer number one. Remember, they're equally good swimmers. They're going to go with the current and then fully against it. Swimmer two, see what I did there? Smart swimmer. They'd actually have to angle upstream, just like we did with boaters. Sorry. They are going to go 100 meters across, kind of fighting the current, and then 100 meters back, kind of fighting the current. So there's our little gun. 3, 2, 1, bang! The gun goes, the swim is on, we're all there watching and cheering. It's quite obvious that this swimmer is going to cover the first 100 meters quicker. So we're watching these two swimmers and we go, oh my gosh, swimmer number one hit the bell first. Swimmer one is in the lead. But if these are equally good swimmers, it actually turns out that there is going to be a winner. They will not tie. And the winner has simply chosen the faster route. And the faster route in this case, by a little bit, is to fight the current a little bit both ways. So these two swimmers, although they're equally skilled, it's swimmer two who went across this way and back who's going to win that race every time. It's quicker to go at 90 degrees to a current than it is to go with the current and then fight back against it. So people knew about this. Scientists knew that this is true as well. So Michelson and Morley built this interferometer to work on this principle, that they're going to shine some light, and some of the light is going to go with and against the ether, and then some of the light is going to go at 90 degrees to the ether. So there should be a slow pathway and there should be a fast pathway. So we'll flip back to this. Here's how this Michelson-Morley experiment, this interferometer, works. I want you to keep in mind that these fellows spent years and years and years designing this experiment. Huge, huge time investment into this experiment and getting it working properly. So they took a laser. They shone the laser at something called a beam splitter, which is kind of like a tinted window in a car, where you've probably done this. You can look at a tinted window, and if you focus your eyes one way, you can actually get a reflection off of the window. You can use it almost like a mirror to fix your hair or something like that. But if you look at the beam splitter or a tinted window, you can actually see through it as well if you sort of refocus your eyes. So the beam splitter is just this material, like a tinted window in a car, that is sort of half reflective and half see-through, half transparent. So when they shone the laser at the beam splitter, 50% of the light, half the light, is going to bounce off it and strike an actual reflective mirror. So that beam of light hits the mirror, bounces back to the beam splitter. Now I didn't show this part, but some of you might be watching going, oh man, isn't the beam splitter going to dump some light going back towards the laser? Yeah, it is. We're not worried about that part. But the beam splitter will deflect some up towards the mirror, which reflects it back to the beam splitter, and then some of the light's going to go right through the beam splitter into this detector. Now, if we go right back to the start, we shine the laser at this beam splitter, it's going to deflect half of the light up towards a mirror. But remember that half the light's going to go right through, right? It's like a 50-50. It's like that tinted window. So half the light is going to bounce, or sorry, I should say go straight through, pass straight through the splitter, bounce off a mirror, head back towards the beam splitter. Now some of that light will pass right through the beam splitter and go back towards the laser. We're not too concerned about that part of it. We're concerned about the part that bounces off the beam splitter, that reflects, and goes back down to this light detector. So what Michelson and Morley did was they said, hey, we've got this luminiferous ether sort of out in space, right? The whole universe is full of this stuff. And because Earth is moving through this ether, there's in effect an ether wind or an ether current flowing over the Earth. It's the same how if there's no wind outside, but you start running really fast, or you hop on your bike and you start pedaling fast, you feel a breeze, and I'm saying that in air quotes, even though there is no breeze. It's just because you're plowing through the air. So Earth is orbiting around the sun, plowing through this ether. So there's like an ether wind passing over the planet. Let's say it's going that way. So they designed this experiment. They tested it for like 4 months straight. From, what was it, April to July of 1887. So several years to get this thing built. 4 straight months of testing, and they tested in like every scenario they could think of. They should have had, if there's this ether sort of wind going one way, they actually didn't know which way the ether sort of wind, and again, every time I say wind, think of me using little air quotes. Get it? Wind, air quotes? Sorry, another bad joke. They didn't quite know which way Earth was plowing through the ether, so they just did the experiment like in 1 degree increments. Until they could get it into this scenario, where we should have a slow beam. Remember the beam that goes with current and then fights against it should be a little bit slower. So in this picture, the blue beam should be the slow beam. The red beam, which fights that ether at 90 degrees, should be the faster beam. And so you should actually get one beam of light arriving to this detector a little bit quicker than the other one. So 4 straight months of testing after years and years and years of designing and building and perfecting this experiment. They're looking for this, the ether making the rays arrive at different times. Right? And you spin this thing around, you test different days, different angles, all the different scenarios they could think of they tested, right? Different temperatures, what have you. So 4 straight months, literally 7 days a week for 4 months, testing this thing after years of building it. The result was that the light rays always arrived at exactly the same time. Let that sink in for a moment. That means there wasn't a faster beam and there wasn't a slower beam. And the only way that can happen is if there is no ether. And you might be sort of listening and going, what the heck, Heinrich? Like, we copied this down. You just talked about it for like 15 minutes, man. And the result is that there is no ether? Like, what a waste of time. Why did we do that? Sydney, guaranteed, is ticked right now. Sorry, shots fired. Sydney, it's all good. We're friends. There is no ether. Right? Mind blown. Really, really important experiment. Now you have just an inkling of how these fellows felt when they realized that there was no ether. You invested 15 minutes of your life and you're ticked off about that result. Imagine if you had invested like 5-6 years of your life. You find out there's no ether. They actually felt like a failure, although it was super important that they found this. It's called a null hypothesis, when the thing you're looking for, you realize doesn't even exist in the first place. Really important because all of science was working on the premise that there was this random ether out there that was causing light to behave in a certain way, and all of science was based on the fact that there was ether. And had Michelson and Morley not done this experiment and figured out this result, all of science would have been going down the wrong path, right? This assumption that there was this magical, transparent, frictionless fluid in space when there wasn't. And we would have had to go back, because we would have figured it out at some point, right? Somebody would have figured it out. They would have had to have gone back and rewritten a whole bunch of science. So although they didn't get the result they were looking for, it's a super, super important result to find out that ether doesn't exist. Okay, so there we go. Craziness, right? No ether. Important, really important experiment. So, other people sort of looked at this result and said, wow, that's really weird. That is really, really weird, because that means light can actually travel through empty space without some kind of fluid there. No other kind of wave can do that, but light is special. And people started looking into light, other scientists, and they found out that light is special in more than just this way. So here are two assumptions of relativity. These are things we need to know. All of what we look at for the next couple of videos, or next bunch of videos, is going to be based on these two assumptions. Number one, there is no preferred reference frame for light. I'm actually going to come back to that point in a moment. So you can copy it out, but I'm going to leave it for the moment and actually jump us into point 2, and then I'll come back and explain point 1. Here's number 2. The speed of light is always the same, no matter who measures it, where they're measuring from, or if anybody's moving. The speed of light is, since it's a constant, we actually give it a variable, a lowercase c, which I know is the same as specific heat, which we saw in chapter 6, but I'm not going to give you a question about a toaster traveling at the speed of light. So you don't need to worry about me mixing up what the c value is supposed to be. And that value is 3 times 10 to the 8 meters per second. It's really, really, really fast. That number might be worth storing in your calculator, although maybe don't store it as the letter c, because if you run quad formula with the letter c, it'll overwrite it. Maybe store that number 3 exponent 8 as L for light or something like that. What's crazy is the speed of light is always the same, even if things are moving. So we've talked about, way back when we looked at chapter 3 in vectors, we said, hey, if somebody's running at 10 meters per second and they throw a baseball at 10 meters per second, then if you or I were just standing on the side watching this happen and we had a radar gun, we would measure the baseball traveling at 20 meters per second. Because the person was moving at 10 and then they threw the ball at 10. We just add those numbers together. We add vectors. We'd say the total velocity is 20 meters per second. That is not the case with light. If you're just standing there and you turn on a flashlight and somebody has a radar gun, they will measure the speed of light at the speed of light. 3 times 10 to the 8 meters per second. Now, if you hop on a bicycle and start pedaling at 20 meters per second, then you might say, oh, now they're going the speed of light. They turn on the flashlight, right? We've got our radar gun. Wouldn't you just take the speed of light and then add on the 20 meters per second, just like we did for the person running with the baseball? And the answer is no. The speed of light is always just the speed of light, 3 times 10 to the 8 meters per second. So even though the person's moving, you don't add that additional velocity on. If they were moving away from you, then you'd think, oh, we kind of take those vectors away from each other. We subtract them. Not if it's light. Anything other than light, you would add and subtract those velocities. But when it's just light, it's 3 times 10 to the 8 meters per second. Doesn't matter if anybody's moving. It's craziness. So that's number 2, the second assumption, that the speed of light is constant in all reference frames, even if things are moving. Let me go back to number 1. There is no preferred reference frame for light. I want to show you something that looks like the Doppler effect, but now we're going to look at light instead of sound. So we've got a laser that's stationary, and it's emitting some light that has a specific frequency, 4.75 times 10 to the 14 hertz. Don't worry about the number, we'll just go with it. That is the frequency for a red laser. This person here we're going to say is an observer. This is like somebody's eyeball inside view. And they're not staring at the laser. We don't want them to go blind. But let's say they've got a radar gun. They would measure that light getting to them at a speed of 3 times 10 to the 8 meters per second. No surprise there. Speed of light is always the same. And they would measure a frequency of 4.75 times 10 to the 14 hertz. The same frequency as the laser is actually emitting. No surprise. It was like the Doppler effect with nobody moving, 440 hertz, 440 hertz, done. The speed of light, by the way, is 343 meters per second, as opposed to 3 times 10 to the 8 meters per second. So light is so much faster. Just a random Jeopardy fact. Now here's what's crazy. Let's take that laser and put it on a cart and move the cart at 1/20th the speed of light, which is like stupidly fast, right? And that laser still emitting the same frequency light, the same red light. Here's the observer. They measure the light arriving at the speed of light. You don't add the two velocities together, the speed of light to whatever 1/20th the speed of light is, because you just don't with light. Light always goes the same speed. That's crazy on its own. You would actually get a slightly different color, though. You'd get this shift in color. You would record a frequency of 5.25 times 10 to the 14 hertz. Don't worry about sort of how much the number has changed. Just know that it has changed and it's become 5.25 times 10 to the 14 hertz. Now let's take that scenario and flip it. Just like we did for the ambulance at 90, and then we said you move past the ambulance at 90. So let's make the laser stationary and have you move past the laser at 1/20th the speed of light. So here it is. We flip this scenario around. Remember with Doppler effect in sound, it was like 475 and 472. We could tell who was moving because the shift, that Doppler effect, was slightly different. Well, check this out. If you're moving at 1/20th the speed of light towards the laser, you would record the speed of light as the speed of light. No surprise. But you would record a frequency of 5.25 times 10 to the 14 hertz. That is exactly the same frequency as if the laser moved towards you. What that means, and again, maybe it's hard for your brain to sort of figure this out, but I'm just going to say it anyway. And that don't take offense when I say that. Sorry, that didn't sound right. It's a little bit hard to see what's going on here. The frequency has changed, but to the same value. That means if I tell you that somebody's moving at 1/20th the speed of light, you actually can't tell who's moving. What that means, and this is crazy, this is going to be hard for your brain to accept, because it's hard for my brain to accept even now. I've taught this for years and years and years. You can't ever tell who is moving at any time. So right now you could be like, hey, I'm sitting here in a chair and oh look, there goes my mom. She just walked by. You actually cannot prove with science or math that you were stationary and your mom was moving. It is equally valid for your mom to say, no, I'm stationary in space in the universe and you, the ground, moved under my feet. They are actually totally valid when they say that. And sometimes you're like, what? Does that say that again? So you're standing on the side of the road and a car drives by. You'd say, yeah, I was standing there stationary and the car was moving. But you actually can't prove that. It is equally valid to say, no, the car was stationary and the ground was moving under the car. You moved past the car because you're attached to that moving ground, almost like a treadmill, right? Moving under your feet. You actually cannot prove, seriously, you cannot prove with science or math that you were the one that's stationary and the car was moving. It's just as easy to say and just as valid to say that no, the ground was moving underneath the car like a big treadmill. That's craziness, right? There is no preferred reference frame for light, is what we end up saying. We mean that you can't tell who's moving or who's stopped, but in science we actually say that. We say there is no preferred reference frame for light. So that's crazy, right? That takes some time to digest. Yeah. So again, I'd love to chat with you some more in Zoom about this concept because it is crazy. You're probably going to be in denial, hopefully not angry with me, but let's chat. Let's bargain about this in a Zoom meeting. It'd be quite exciting. But it is true, and I'm not pulling your leg. We like to think about things being stationary and other things moving because it's just easier for our brains to figure out. But it's not true, right? It really isn't. You can't tell who's moving. That means when I go for a run, my position in the universe might actually stay exactly the same and the ground just moves under my feet like a giant treadmill, right? I say I don't like running on a treadmill. Well, maybe I'm kind of running on a treadmill every day. And other people will go, whoa, does that mean then that like the whole universe or the whole world could be moving under just one person's feet? And the answer is, yeah, I guess so, right? Like it's totally crazy. Or is the world like moving? How can it move under multiple people's feet at the same time? How can there be like multiple treadmill things happening with the ground? I don't know. We have no way of ever proving like who's the person that's stationary and who's the person that's moving. So when we talk about stuff moving, you can continue to talk about it like we normally would, but know that you can't actually prove it. Mind blown. Super cool stuff, but super crazy. This video is getting kind of long, so I will stop there. We're actually not quite done the first lesson, but we'll just split it into two because we got lots of time. So thanks for hopefully not being angry with me. But please do watch this video, think about this stuff, and join me on Zoom, right? This is a really, really fun unit where if we can get a couple of people together, we can have some really neat conversations. And I really would love to have these conversations with you. So you probably have questions. You probably want to bargain with me, right? What if this? What if that? Hit me up on Zoom. Let's chat about it. I really do look forward to it. So we'll talk soon.